All right, so welcome everyone to the Graduate Online Combinatorics Colloquium. This week we have Venkitesh, who's going to talk about covering symmetric subsets of the cube by affine hyperplanes. Before we start, I just want to mention the community statement rules that we go by. We're all learning, everyone has something to contribute, and no one has all the answers. So with that in mind, let's welcome Venkitesh.
Thank you. So yeah, hi. I think I've been here last year as well, around this time, or maybe a little while later, maybe in May or something, to give a talk. And it's good to be back again. And thanks for this chance. And for those of you who have not seen me before, I'm from India, from Mumbai, from IIT Bombay, and yeah, it's good to have this chance to meet you guys and present my work from last year, whatever I've done. So this is essentially my research work during the COVID lockdown. So let's see how it goes. So the title is covering symmetric subsets of a cube by affine hyperplanes. Let me begin by saying that the title is a ripoff from another paper by Alon and Shuredi, which was titled Covering the Cube by Affine Hyperplanes. And that's where we start. So let me mention right at the outset, the field that we are working with is the reals. We are not concerned with positive characteristic. The questions can be asked in positive characteristic, but the answers are just much more subtle. And we do have some partial progress over positive characteristic, but maybe not good enough to present it at the moment. But yeah, we'll give complete answers to some of the questions that I propose over the reals. So let's start with a classical hyperplane covering problem. And this was solved completely in the paper by Alon and Shuredi. So what is the problem? Well, you start with the Boolean hypercube, which we represent by 0, 1 to the n. And the question is, if you start covering the hypercube with hyperplanes while making sure that you exclude exactly one point, how many hyperplanes do you need? What's the minimum number of hyperplanes that you require? And Alon and Furedi proved that any family of hyperplanes that covers the hypercube except one point, there's nothing special about the all zeros point, so except one point, must contain at least n hyperplanes. Let me just clarify this notation. 0 to the n means the zero vector of length n, just an abbreviation. So any family of hyperplanes that covers a hypercube except one point must contain at least n hyperplanes. And we are going to try to extend this problem to what I call symmetric subsets. So before we go there, let me just mention a few related results. There has been some very interesting work last year. So let me just mention those. So what are the extensions and variants that we know of? This is not an exhaustive list, just some of them. So last year, Clifton and Huang considered a multiplicity extension of this problem, where the question is to cover all points of the hypercube except one point k times and exclude the exclude one point completely. And in this case, they give tight bounds when k is equal to 2 and k is equal to 3, and a lower bound of n plus k plus 1 when k is at least 4. There was a relaxed version of the same problem proposed by Sauerman and Wigderson, where instead of hyperplane covers, they considered polynomial covers. So now the question becomes, what is the least degree polynomial which covers every point of the hypercube except one point with multiplicity k, while excluding the single point completely, in this case the origin. Sauerman and Wigderson actually considered a slightly more general version, but I'm just mentioning this special case here just to keep things nice. And they gave a tight bound for this relaxed version, which is n plus 2k minus 3 when k is greater than or equal to 2. Another variant of this question from about 15 years back was by Lineal and Radhakrishnan, who proposed something called an essential hyperplane cover. Now, what is this? This is a hyperplane cover for the whole of the hypercube. Points are not excluded. You're supposed to cover the full hypercube. But every variable should be influential. So when you think of the hyperplane cover as being represented by a polynomial which is a product of linear factors, Every variable must find its presence in at least one linear factor that forms that polynomial. And we have a bound of order n on the upper side and square root n on the lower side, which was proved in their paper itself. And we don't have any improvement over this, even after 15 years. The only mild improvement that we have was by Saxton in 2013, who gave the tight bound of n plus 1 when we restrict our attention to hyperplane covers where the hyperplanes are represented by linear polynomials having non-negative coefficients for every variable. The constant term in those could be negative, that's fine, but the coefficients of the variable should be non-negative. When you keep impose this restriction, well, it's a slightly different problem now. Even the upper bound gets pushed above, and the tight bound is now n plus 1. And an intuitive way to understand this condition of non-negativity on the coefficients of the variables is that essentially all the hyperplanes are now oriented very similarly. All right. So that is a different variant of this covering problem. And another interesting question that was considered last year was by Aronson and a few others. And they call it an exact hyperplane cover, which is also fairly intuitive. You fix a subset and you're supposed to cover the hypercube except points in the subset. So cover every point of the hypercube except the subset. You're supposed to exclude the subset completely. So any collection of hyperplanes that covers 0, 1 to the n minus s and no point in s. It's an exact hyperplane cover for s. And they characterized tight bounds for s whenever the size of s is at most 4 and gave asymptotic bounds in the general case. So this is where I'll wrap up the description of related literature. As you see, last year has been really good as far as working on this problem is concerned. We have had some really interesting variants popping up and some really good results coming through. Now let's consider our problem. So let me begin with the basic definition. So the Boolean hypercube is denoted by 0, 1 to the n. Box n to me is the subset 1 to n. And for any x in 0, 1 to the n, the Hamming weight of x is defined to be the number of ones in that vector. All right. Now this is a very useful quantity, the Hamming weight, because so to start off with, a subset of the hypercube is said to be symmetric if it is invariant under permutations of coordinates. So formally speaking, you start with x and apply any permutation sigma on n letters, the permuted element must also be in the set. And this is where the Hamming weights come into the picture. They give us a very nice characterization of symmetric subsets. A subset is symmetric if and only if there is a subset of 0 to n. There is a small abuse of notation here. When I say interval 0 to n, I mean the integers only, the integers from 0 to n. So a subset of the hypercube is symmetric if and only if there is a subset of the integers between 0 to n such that S is equal to the set of all 0, 1 vectors with Hamming weights in E. And the interval 0 to n makes sense here because when you have the n-dimensional hypercube, the range of values for the Hamming weight of any vector is between 0 and n. So a very neat diagrammatic way to understand this is the following. So for instance, let's take a 20-dimensional hypercube, and a symmetric subset is essentially a collection of what I call layers. So the Hamming weight enables us to partition the hypercube into layers, one layer for every Hamming weight, right? And now I am collecting layers with Hamming weights 6, 7, 8, 10, 12, and 15. And instead of representing them as subsets of the hypercube, this is just a subset of the interval 0 to 20 indexed by the Hamming weights. Okay. This notation is really very useful to us because the first thing that we're going to see is that when I introduce a closure operator, the closures of symmetric sets will again be symmetric. And therefore, we can essentially forget the hypercube as such and just talk about subsets of 0 to 8. That's the convenience that we'll encounter. So let's go ahead. What is the question that we are going to consider here? So let's start with a subset E of 0 to n. And this is a one-to-one correspondence. Subsets of 0 to n are in one-to-one correspondence with symmetric subsets of the hypercube. Let's start with a subset E. The only thing to note here is that we are concerned only with proper subsets because we want to consider hyperplane covers of proper subsets, not the hypercube. So a proper subset of the hypercube represented by E. And let me just take two copies because I'm going to talk about two problems here. We'll extend the Alan-Fioriti question in two different ways. So as a collection of layers, this is what they look like. The first question is the following. So I can take a collection of hyperplanes which covers the set E, by which I mean it covers all the points with Hamming weight in E. So a set of hyperplanes which covers the layers in E, but does not cover the full hypercube. In other words, it excludes at least one point in the complement of E. Right? In this case, it's this red point. Could be anywhere. Need not be the all zeros point or the all ones point. Some point in the hypercube. That's it. But this is a non-trivial hyperplane cover because it covers the symmetric subset E, but does not cover the full hypercube. So it's a non-trivial cover. All right. The second variant is a stronger restriction on the hyperplane covers. I can start with a collection of hyperplanes that covers the layers in E, but among all the layers that are outside E, in every layer, at least one point is excluded. What is the difference here? Well, in the first variant, when we consider non-trivial cover, we only impose the condition that the full hyperplane should not be covered while covering E. Whereas when we consider a proper hyperplane cover, first thing to note is that the complement of a symmetric subset is again a symmetric subset because it's just indexed by the Hamming weights which are not in E. And now here the restriction is that this hyperplane cover should cover every layer in E and not fully cover any layer that's outside E. So for every layer that's outside E, at least one point is excluded. So these are the red dots corresponding to the layers which are not in E. All right. So I don't mind pausing here for a moment because I believe this figure is probably the easiest way to understand these two definitions. So let me pause here and have a look at this. And if there is something that's not clear, I'm happy to answer.
So just the most general definition, what does it mean to cover the cube with hyperplanes?
Oh, right. So I'll say a point of the hypercube gets covered by a hyperplane arrangement if the point lies in the zero set of one of the hyperplanes. The polynomial is representing one of the hyperplanes. It has to be in the solution set of one of those equations. That's it. So geometrically, the point passes through one of the hyperplane. One of the hyperplanes passes through that point.
Okay, and so you're interested in the lattice points, and these are these affine hyperplanes, or do they have to go through the origin?
Oh
Probably.
no.
I assume.
They are
Yeah.
affine hyperplane. Yeah.
Otherwise,
Origin. Yeah, it's
you
too
wouldn't be
tight.
able to skip the origin point. Yeah.
That's right.
So you
That's
have a
right.
bunch of affine hyperplanes you're trying to hit. You're trying to have the hyperplanes run into all of the points in
That's right.
the that are lattice points of these hypercube. Okay.
Right. And algebraically, the neatest characterization for this is that a collection of such hyperplanes, let's say k of them, it will exactly correspond to a polynomial of degree k, which is a product of k linear factors. So it's a polynomial, a hyperplane arrangement to me in this context is just a polynomial that's a product of linear factors. And that's essentially what we'll use when we go ahead. All right. So I hope so much is clear. The definition is clear. Shall we go ahead?
One tiny question. So earlier you were
Yeah.
talking about the closure of the set E. So in this example, what would the closure be?
Oh, very nice. So it also depends on the degree. So for small enough degree, the closure of this set will include the points 0, the Hamming weights 0, 1, and then the Hamming weight n. So as we shall see a little bit later, the closure of any subset will always look like, well, the set itself and a few initial layers and a few final layers. A few layers from the bottom, continuous, and a few layers from the top, continuous. Every closure of every symmetric subset will have this form. Okay, so that's essentially an offshoot of what we'll see a little while later. We'll come to it.
Okay.
Stella, what do you mean by a closure?
Right. So I'll just define it in a few slides. The closure phenomenon is very similar to what we encounter in classical algebra. You take a set of points and look at the set of polynomials from a mother collection which vanish on this set of points, and then take their common zero set. That is a closure. But I'll make the definition more precise. It just turns out that we are not, the mother collection of all polynomials is not the polynomial ring for us. Instead, it will be the collection of polynomials representing hyperplane arrangements. That's the difference. Okay. So, all right. So let's go ahead. And so, yeah, this is the definition once again in words. So if we have a proper subset of 0 to n, a family of hyperplanes is a non-trivial hyperplane cover if E is contained in the union of, if E bar corresponds to the set of points in the hypercube with weights in E. So if E bar is contained in the union, and the union of these hyperplanes intersected with the hypercube is not the full hypercube. So it doesn't cover the full hypercube. Whereas a proper hyperplane cover, again, it covers the set E or E bar, and for every element that's not in E, which means for every Hamming weight that's not included in E, the corresponding layer is not fully covered by this arrangement. That's it. So now, recapping to this figure, what are we interested in? The same question. What is the smallest size of a hyperplane cover that satisfies the appropriate condition? So HCN of E will denote the smallest size of a non-trivial hyperplane cover for E bar, and PHCN will denote the smallest size of a proper hyperplane cover for E bar. All right. So what is our result? Well, we propose this question here, and we also give a full characterization. Okay. So let me start with an abstract set operator here. Okay. So now, as I said, we will sort of very freely work with subsets of 0 to n because the closures, we are essentially in the world of symmetric subsets. Even when you take the closure, it will again be a symmetric subset. So for any fixed degree D and a subset E, which I have enumerated in the linear order T1 to Ts, I define an operator Ln comma D on E. What does it do? Well, if the size of E is at most D, it doesn't do anything. It's E itself. If the size of E is at least D plus 1, then we include E as well as an initial segment and a final segment. So the initial segment and final segment specifically look like this: 0 to T S minus D and T D plus 1 to N. So in this case, S is at least D plus 1 because S is the size of E, right? So why this operator, we'll again see in a little while. It's very intuitive once we get to the heart of the technique that we're employing. To not keep you in complete suspense until we reach the main point, let me say all of this essentially builds upon the Alon-Furedi bound. And we are just using some more additional machinery, but at the heart of it is one crucial lemma which uses the Alon-Furedi bound. All right. So what's our answer? So we are interested not in one application of this operator, but several applications of this operator. We'll start with the set E and keep applying this operator again and again and again on the set. All right. And then, well, this set potentially grows because a k plus 1 application of the operator L will contain what you get when you apply k applications of L. So this is a growing chain in the poset of all subsets of 0 to n. So wherever the chain terminates, we are denoted by L bar n comma d. L bar n comma d is a union k greater than or equal to 0 ln dk of E. Slightly Probably a slightly inconvenient notation, but things will just get easy in a little while. Why do we bother about any of this? Well, here's the main theorem. For any proper subset, HCN of E is exactly the smallest d for which L bar d is not equal to 0 to n. And PHCN of E is exactly the smallest d for which L bar d of E is equal to E. And this is what I mean by a combinatorial characterization, because this is just a plain set operator. All right. And one of the things that I have not really elaborated on in the further slides, let me just mention it here. One key point about this characterization is that now this number can be computed efficiently, because when you look at the expression of L, one application of L can be computed in something like order n time, because we have this nice representation. It's 0 to ts minus d union e union td plus 1 to n. And we just keep applying it for varying d's and sort of pick the minimum. So both of these quantities can be computed in something like order n cube time. All right. So this one of the offshoots of this characterization is that these numbers, even if they cannot be computed by hand, they can definitely be computed efficiently with an algorithm. Okay. So that's the first thing. Why do we care about this operator? How does it pop up? Let's go ahead and see. So that's where I introduce a new class of closure operators called finite degree hyperplane closures. It's very similar to the idea of closures that you see in classical algebra, but we just change the collection of polynomials that we are concerned about. So let me denote by script hn the set of all polynomials in the polynomial ring Rx1 to xn, which are products of linear factors, including the constant polynomials, just to keep things nice. Essentially, Hn is a collection of all hyperplane arrangements, to put it in the simplest of terms. Every hyperplane arrangement is a product, as a polynomial is a product of linear factors, and I've just collected all of them. Okay. And now for any subset, I can just define Hn of S to be all those polynomials which vanish on S. In other words, all those hyperplane arrangements which cover S. Right? And Hn comma d of S is all those hyperplane arrangements with at most d polynomials, with at most d hyperplanes, or in other words, the collection of all hyperplane polynomials with degree at most d. All right. And now the degree d hyperplane closure of the set S is just defined to be the common zero set of this collection inside the hypercube. We are concerned with the hypercube. Okay. So what is this? Well, in words, start with the set S. Look at the collection of all hyperplane arrangements with at most d hyperplanes that contain the set S, and then take their common intersection. Okay. And this will turn out to be a symmetric set. So this is an easy observation and just follows by tracing the definition. So I'm not mentioning the proof here. For any degree and any subset, the hyperplane closure of degree d for the set E bar will always be of the form F bar for some other set F. It will be a symmetric set. And therefore, we just drop off these bar notations and we'll just talk about closure of a subset of 0 to n. Okay, we'll just denote this as hyperplane closure of E is equal to F. So we'll just forget that we are working with layers. Instead, we'll just work with subsets of 0 to n, just for convenience. Okay. So now, why are we interested with hyperplane closures? How do they connect with what we have seen just now? So let me just recall. Non-trivial hyperplane cover is a hyperplane arrangement which covers E but excludes at least one point. A proper hyperplane cover is a hyperplane arrangement that covers E but excludes at least one point from every layer that's not in E. HCN is the smallest size of the smallest non-trivial hyperplane cover. PHCN is the size of the smallest proper hyperplane cover. And how do hyperplane closures connect with the numbers? This is the definition. This essentially follows by definition. So let us trace the definition of the covers that we have and convince ourselves that this is true. So take any D which satisfies the property that the degree D hyperplane closure of E is not equal to 0 to n. It essentially means there exists a hyperplane arrangement with at most D hyperplanes that contains E and does not contain the full hypercube. Therefore, it's a non-trivial hyperplane cover. The converse is also true. We start with a non-trivial hyperplane cover, look at its corresponding polynomial, it will fall here. And therefore, the smallest size of a non-trivial hyperplane cover is exactly equal to the smallest degree corresponding to which this hyperplane closure is non-trivial, not equal to 0 to n. Right? And now, similarly, or in the second case, we don't just exclude one point, we now exclude one point from every layer that's not in E. So the closure cannot contain completely any layer that's outside of E. And therefore, the degree D hyperplane closure of E should be equal to E if there is a proper hyperplane cover of size D. All right. So this is the characterization of these two numbers that we're interested in terms of the hyperplane closures. So I think once again I'll pause here, and if you're not convinced of this, I'm happy to elaborate. Is that all right? Will I go ahead?
I don't have any questions.
Okay. Okay, so let's go ahead. So what have we done so far? We have introduced a new set of closure operators called hyperplane closures and characterized the smallest set of the two variants of hyperplane covers that we're interested in terms of the hyperplane closures. Right? That's all we have done. But our main statement does not concern with the hyperplane closures so far. It concerned with something else, a set operator called L bar. So how do these two connect? So that's our main theorem. It's a combinatorial characterization of the hyperplane closures. So just what we saw in the last slide, the two numbers HCN and PHCN for a subset E is characterized in terms of the hyperplane closures here. The main theorem said that HCN and PHCN can be characterized in terms of the operator L bar. Right. So what do you expect? Under what conditions are these two really going to be compatible with each other? That is the combinatorial characterization I am referring to. So for any degree and for any symmetric subset, the hyperplane closure is equal to whatever you get when you apply the operator L bar. All right. So let me just rewind to the definition of L bar a few slides back. L bar is repeated application of the operator L corresponding to the degree D. And all it says is we start with a subset E, a symmetric subset. And I keep applying the operator L in a greedy fashion. I keep applying it. At some point, the chain that is generated must stabilize. I will reach a stage where if I apply the operator once again, I'm not going to add any more point. Wherever I stop, that is equal to the hyperplane closure. Okay, that is what this means. So let's go ahead and so what comprises the proof of this? And there is a very small lemma, a cute lemma actually. It's more or less a neat consequence of the Alon-Furedi bound, and the lemma, in some sense, sheds light on why this machinery should work the way we expect it to work. So this is what I call a closure builder lemma because intuitively for me, repeated application of L, the operator L, is a means of building the closure of E, the hyperplane closure of E, step by step. Okay. So what does it say? Well, start with a subset of 0 to n with size at least d plus 1. And why is it d plus 1? Well, if we go back to the definition of L, when the size of E is at most d, we don't do anything. We don't add any layers. So let's start with a subset of size at least d plus 1 and let A be the minimum of E and B be the maximum of E when you write it down as subset of 0 to n under the usual order. Then everything from 0 to A and everything from B to N must be in the hyperplane closure. This is what I referred to a little while earlier. The closure will look like the set E along with an initial segment and a final segment, if you think of it as a subset of a 0 to n. All right. So these essentially are components of the initial segment and the final segment, which we'll get at the end. This may not be all. There may be more, which we'll get by repeated application of it. But so far at this stage, this is what we have. And what do we mean by the operator L? Well, L essentially captures this lemma, which we'll see in a little while. But let me quickly prove this. How is this a consequence of the Alon-Furedi bound? So it turns out that I need to prove only one special case. So let me start with an element to the right of E, which is possibly not in the closure. I claim that everything to the right of E is in the closure. That's what I mean when I say B to N is in the closure. Right? So suppose there is a J that's not in the closure of E, and the special case I take is J equal to N. That's enough. The rest of the proof can be reduced to this case. So let J be equal to N. So the layer N, which is just one point, the all ones vector, that is not in the hyperplane closure of E, which means there is a polynomial of degree at most D, but it's a product of D linear factors. In other words, there is a hyperplane arrangement with at most D hyperplanes that covers the set E bar, but does not cover the all ones point. And this is how we are getting closer to the Alon-Furedi bound. So what do I do? Well, this is a hyperplane covering the layers in E, not covering the all ones point. I leave out the all ones point. Look at the remaining layers which are not covered for the moment. And I just take the corresponding hyperplanes which cover those. So the additional linear factors that I multiply with P here to get this polynomial Q is essentially a modification to this hyperplane arrangement. I start with the original hyperplane arrangement and add a few more hyperplanes so that the modified arrangement covers every layer from 0 to n minus 1 and still excludes the all ones point. That is exactly what I mean by this multiplication of linear factors. Right? But what is this? This is now a hyperplane arrangement that excludes the all ones point and covers everything else. So by the Alon-Furedi bound, there must be at least n hyperplanes here. Right? So the degree of this polynomial must be at least n. Right? But what is the degree? Well, let's count. The degree of Q is at most the degree of P plus n minus mod E. The number of linear factors that we have added is n minus mod E. But mod E is at least D plus 1. So this sum is only at most n minus 1. And that's the contradiction. Right? The Alon-Furedi bound says the degree has to be at least n. But here we get only n minus 1. Therefore, what we started out with is not correct. Everything to the right of E must be in the closure. And similarly, we can just employ a reflection argument and say that everything to the left of E must also be in the closure. Okay, so that's how we are essentially making use of the Alon-Furedi bound once again. Is so much clear? Anything that's not clear in the proof? Okay, so let's go ahead. So why do we care about this lemma? This connects exactly with the operator LD that I was mentioning earlier. So if we start out with a subset of size at least d plus 1 and enumerate it as t1 to ts, LD has this compact representation. It's a union of E along with the initial segment 0 to ts minus d. and the final segment kd plus 1 to n. However, this is also equal to this larger union where you vary across all d plus 1 sized subsets of E and add the layers which you get by applying the lemma. Okay, so lemma says you pick any subset of size d plus 1 of E, and let's call it A, everything from 0 to the minimum of A and everything from max of A to n should be in the closure of A. But A is a subset of E and it's a closure operator. So all of these are going to be in the closure of E. Right. So the operator L here is just a compact way of representing greedy application of this lemma to d plus 1 subsets of E. Okay, that's one step. And now we have potentially added a few more layers to the closure. So we will again apply this lemma to the larger set. And that's how we build and reach up to L bar. Okay. So far, modulo the main theorem, we have actually answered our question. Because what did we do? So let me just quickly recap. Yeah. So the definition of the hyperplane closures gives us a characterization of these numbers in terms of the hyperplane closure. The hyperplane closures are characterized by the operators L bar because we have just seen because we have essentially seen an outline of the proof. An iterated application of L gives us the hyperplane closure, although not the full proof. And this characterization enables us to get the final statement, right? This characterizes the two numbers combinatorially in terms of the operator L bar D. All right. So we can actually simplify this further. So this is what we have right now. I have not yet proved the main theorem. I have not completely proved the combinatorial characterization of hyperplane closures. I'll get to it towards the end. But modulo that, this is what we have. We have proved this now. The size of the smallest hyperplane cover for the two variants is given by this characterization in terms of L bar. Turns out that these two conditions are very special. We can actually simplify these two conditions and write it in an easier fashion. So for any I, let me just call T n comma I to be the union of the two initial and final segments of length I, 0 to I minus 1 and n minus I plus 1 to n. Okay, and for I less than 0, I'll just call it empty set. So the characterization is that L bar D of E is not equal to the full hypercube, 0 to n, if and only if there is an I in 0 to D, such that E union Ti is not 0 to n. And the size of E minus Ti is at most D minus I. It's an easy consequence of the definition. So, which is why I'm not going into the proof of it. Easy consequence of the definition. And the second condition is even easier. L bar D of E is equal to E if and only if a union of initial and final segments of length mod E minus D is contained in E. A union of two caps is contained in E. What does this give us? It gives us an easier characterization. So now HCN of E is a minimum D such that this condition holds. There is an I between 0 to D such that E union Ti is not 0 to n and size of E minus Ti is at most D minus I. And PHC of E is an even nicer characterization. PHC of E is equal to size of E minus max of I such that Ti is contained in E. So probably HCN is a little more mysterious in terms of the characterization. I really couldn't simplify it any further, but PHC is just beautiful. All it says is if you want to find the smallest size of a hyperplane cover that properly covers the set E, simply look at the largest union of initial and final segments that is contained in E, okay, of length I, and just subtract it from the size of E. That's equal to the size of the smallest cover. That's it. Okay, so this is the neat characterization, and it, it might not be obvious for HC, but for PLC it's really obvious. What happens to the Alon-Furedi case? In the Alon-Furedi case, let's say we are excluding the all zeros point. So the layers included in E are 1 to n, right? So which Ti is contained in E? No Ti is contained in E because Ti always is a union of an initial segment and a final segment. So it must contain 0 and n, right? But E for us in the Alon-Furedi case is 1 to n. So 0 is not contained. Therefore, no Ti for I greater than or equal to 1 is contained in E. Only T0 is contained, and T0 is the empty set, right? So this maximum is 0 because I is equal to 0, and we get PHC of E is mod E, which is the Alon-Furedi bound. Okay, so this is a more general statement in that sense. So let's go ahead. In fact, I want to show you another application of this characterization. We made use of this characterization to solve this hyperplane covering problem. We'll use this characterization to solve another problem. We'll give an alternate proof of a lemma used by Alon and a few others in the context of a balancing problem. Okay, why did I choose this application? It's because this application serves as a good illustration of the proof of the main theorem that we have. So I will not prove the main theorem in full detail. Instead, I'll just illustrate its proof via this application. Okay. So we are going to another problem now. So before that, so far, is there something that's not clear? Okay, so now we just change the representation for convenience. Now the Boolean hypercube is -1, 1 to the n. It's not a big difference because it's just an invertible affine change of coordinates. So the closures will get mapped to closures and there's no problem. The Hamming weight of a vector, a -1, 1 vector now is the number of -1s. Okay, so our hyperplane closure results hold for this representation as well because we can look at this invertible transformation where xi goes to 1 minus 2 times x. Okay, and all the results that we have can be mapped to this hypercube. Okay, so now let me just introduce two subsets. What am I interested in? I'll take n to be even, and I'm collecting all the even layers and all the odd layers. Okay, all the layers with Hamming weight even, all the layers with Hamming weight odd. And the lemma of Alon and others says that if there is a polynomial that is non-zero as a function of the hypercube and vanishes, for instance, on the set of all even layers, then its degree must be at least n by 2. Similarly, if there is a polynomial that's non-zero as a function of the hypercube and vanishes on the set of all odd layers, then its degree must be at least n by 2. Okay, so what is this in our notation? Well, in our notation, we can see that we can show that this is equivalent to the following two statements. The degree n by 2 minus 1 hyperplane closure of E0 is 0 to n. And the degree n by 2 minus 1 hyperplane closure of E1 is 0 to n. What does this mean? Well, it means if there is a hyperplane arrangement with at most n by 2 minus 1 hyperplanes that covers all the even layers, then it must cover the full hypercube. Similarly for the odd layers. Okay. So now we already know this characterization, and therefore in terms of L bar, this is the statement. So how do we prove this? We give an alternate proof of this. And I claim that the proof of these two statements are essentially an illustration of the proof of the main characterization. That's exactly what we do. We essentially apply the operator LD greedily. So how greedy can we be? So let me just prove it for even layers, and let me just show it for a concrete example. Let me take n to be 10, the degree d to be 4. The initial lemma that we proved using the Alon-Furedi bound says that for any subset E of size at least 5, everything from 0 to the minimum and everything from maximum to 10 must be in the degree 4 hyperplane closure. Right. So let's start with this representation. The set of even layers in an 10-dimensional hypercube is this 0, 2, 4, 6, 8, 10. Right, and the degree is 4. So if we want to apply our lemma, we want to take subsets of size at least 5, right? So let's take this subset 0, 2, 4, 6, and 8. This is a subset of size 5. The lemma says everything from the left 0 to the minimum, but here the minimum is 0, so I cannot add anything. But from the right side, everything from 10 to the maximum is in the closure. So the 0.9 gets added. Right. Now what do I do? Well, I change sides. I take the subset while excluding the left end. Now once again I repeat this. Now from the left hand point, the lemma says that 1 must get added to the closure because the set I started with has 6 points. Right? And now I iterate. I just alternate the sides and iterate. So eventually, in an alternating fashion, we will end up with every point being in the closure. All right, that is a proof of this. And this is essentially a much easier proof of the lemma. How does this also illustrate the proof, the main theorem? This is exactly what we do when we want to compute the hyperplane closure of an arbitrary symmetric set using the operator LD. We simply start off with subsets of size d plus 1 and alternate in a greedy fashion and keep going, keep adding points as far as we can. There will reach a stage when either we have covered all points, in which case the closure is the hypercube, or we cannot add any more points even after applying this operator. So wherever the chain stabilizes, that is equal to the hyperplane closure. Right. So that's the illustration of the proof. And yeah, I think this is a good time to end the talk here. So yeah, I've covered whatever I wanted to. So yeah, any questions? If something is not clear, I'll be happy to clarify.
That was an awesome talk. I have a couple of questions, so I'll enter them into the chat. Oh,
Sure,
wait,
yeah.
sorry. We should probably thank you the first time. I'm such a sorry.
Oh, thanks.
That was,
Yeah, great talk. Everyone can do the clap stuff or reactions or whatever you want. And yeah.
So I had sort of 3 sort of basic questions, and I'll ask them verbally. I've also entered them into the chat.
Okay.
One, so one of, I don't know which is easier, but so one of them is that some of the energy behind this closure operator seems to come from constructing an algebraic variety and sort of studying that the risky closure of that variety.
That's right.
And so me being someone from Minnesota, I see someone doing stuff with algebraic varieties, and my immediate question, like, oh, is there some statement about rings and ideals hiding in the background that I should be thinking about?
Yeah, that's a good point. So the idea of defining this closure is very similar. The only distinction is now we don't consider the vanishing ideal of the set of points. So if you take the vanishing ideal, what you get is the Zariski closure. Right? And when you restrict it to all degree d polynomials in the vanishing ideal, you get the finite degree Zariski closure, which is what I was mentioning in the abstract. So if you noticed, or if you did not notice, the term finite degree Zariski closure appeared in the abstract but not here. I'll get to that in a moment. So it turns out that for symmetric subsets, I have not proved it here, but it's a fairly straightforward proof. For symmetric subsets, for any degree, the hyperplane closures coincide with Zariski closures. And which is why, in fact, the alternate proof of Alon's lemma works, because if you note, I did jump the gun here at this point. The first statement mentions an arbitrary polynomial, not a product of hyperplanes. But I said it's equivalent to considering a product of hyperplanes. That's because this statement is about Zariski closures. But one can prove that Zariski closures are equal to hyperplane closures for all symmetric subsets. And it's a fairly significant point in the contrapositive sense. So for instance, if you start with a set of points, a symmetric subset, and if you know that a layer is not in the closure of that set, not in the Zariski closure of that set, it means there is a degree d polynomial that vanishes on the set of layers, but does not vanish entirely on the layer that you chose. Right? So it's a witness polynomial of degree at most d that vanishes on the set of layers, but not on the additional layer that you choose. However, the equality between Zariski and hyperplane closure says that, well, now you get a witness polynomial that's a product of linear factors. And that's a much more structural result. Interestingly enough, I don't know of an algebraic proof of it.
Oh,
This equality follows right from this combinatorial characterization that we have been mentioning. The proof that I know of the equality says that, well, hyperplane closure is equal to L bar, Zariski closure is equal to L bar, therefore hyperplane closure is equal to Zariski closure. I don't know of a purely algebraic proof. And yeah, so to answer your first question, I guess, uh, we essentially restrict to hyperplanes because, well, the focus was the hyperplane covering problem. And initially, even I wasn't sure if the hyperplane closure is equal to the Zariski closure. After all was said and done, I just observed at the end that, oh, well, they're equal for symmetric subsets because turns out that L bar also characterizes Zariski closures for symmetric subsets.
cool. I feel like there's a follow-up question, but I want to think a little bit more before I announce that there's a follow-up question here.
Sure.
That's a pretty cool result, that you have these two notions of closure and they're the same, especially because, so this is my second question, which is that your PHC notion, I think PHC, has a little bit of a flavor of like a matroid closure operator. And so I would be curious, is this like equivalent to some notion of, is there some matroid that like this is the closure operator on that matroid?
I haven't thought about it in terms of matroids. Maybe there is. I really haven't thought about it. No. There might be something. I'm not sure. I'll have to see. Yeah. If you find something, let me know. I'll spend some time on it. Let's see.
Yeah, and my third question was like more broadly, like if there was some matroid hiding in the background, is there some matroid property that replaces symmetry? So instead of having like a symmetric subset of this like symmetry, I don't want to say a symmetric subset of hyperplanes, like is there some matroid property where it's like this matroid has, I don't know, XXX property, and then it turns out to be a symmetric subset?
Oh, okay. That's interesting. Well, I'm not sure if there is a matroid hiding in the background, first of all, because I have not thought about it at all from a matroid point of view. But now I'm just shooting in the air. A probable candidate, a probable condition is that, for any independent set, a permutation of the coordinates, a permutation of the elements of the ground set, whatever you get will again be independent. That's not necessarily true. So it's like a symmetric matroid maybe. For every independent set, the permutation of elements is again independent, probably something like that.
Well, hello. If you're looking for a matroid, a matroid that appears in this that appears is the matroid of the the hyperplanes considered as an arrangement of hyperplanes.
Uh-huh.
So your hyperplane cover is a collection of hyperplanes, and as such, consider it to be a so-called, the literature, the name is arrangement of hyperplanes,
Right.
and those things have matroids.
Okay.
The concept is the closure operation, the matroid closure. Let's see. A set of a set of the hyperplanes. Let's see. The closure of a collection of hyperplanes is the let's see. The hyperplane can. The hyperplanes that contain the intersection. Yeah. But that's this is the matroid, a matroid that is lurking in the subject.
I see. I see. Interesting.
Seth, just as a heads up, your microphone is a little bit hard to hear from. I mean, we could kind of understand you. But
Yeah, that's right. Yeah, I can see why.
Yeah, but that's interesting. If there is a connection with meteorites, it would be very interesting. I've just not thought about it from that point of view so far. But yeah, very interesting. Thanks. Yeah.
So I have a question about the Hamming weight. So in the first half, you were counting the i's such that the xi equals to 1. And then in the second half, you were counting I such that xi equals to -1. So
Right.
how do you choose what sort of things that you were counting based on the things you were trying to apply your theorem?
Yeah. So this is it's more or less a choice by habit, and there's no particular reason. So I could define Hamming weights in terms of number of zeros. It wouldn't really matter. And in the -1 case, I could define the Hamming weight as
Venkitesh freeze for everybody or just me? Okay.
He's also frozen for me. Good.
well, seeing that it's 2, maybe we'll pause or we'll stop the recording, but keep the questions going. So if anyone needs to go, feel free.